Good morning, team. Let's see here. All right, I want to just to improve your thinking before we start on this project quickly, my friends, do project 2, which many of you got right, but I just think it would be helpful to at least reason about it in hindsight, even for those who did get it right and feel pretty good about it, sort of quickly. So I have before me prepared a quick drawing. And I just think, as I mentioned yesterday, it's just such a challenge to learn to conceptualize kind of shells and washers. And this is such a cool problem because, you know, it's at least an object that you've encountered in the world, even if you're not a hippie. Thanks for the cool hippie drawing, by the way, Cheyenne. And then the fact that you can actually take the integrals, I mean, that's kind of actually unusual. If you conceptualize a cool problem, well, like the buoyancy kayak problem, like you end up with an integral that you need to take, but you can't take it. Like that's actually fairly common. So anyway, quickly, let's see if we can create, and by the way, I'll offer this as an extra credit. You know, we answered this for a particular size bead with a 42-inch diameter and a 6-inch diameter hole drilled through it. But if you want to, for extra credit, redo this problem with kind of capital R and lowercase r, like this shape is capital R radius and this cylinder is lowercase radius, and like come up with a formula, like the generic formula for all beads. And as I mentioned before, like that's why in one respect you don't see, like if you go ask people, do you use calculus? You use calculus, you're going to get no, 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 no every single time. And one of the main reasons is because calculus gives us formulas for things like this. So, you know, if a bead was something that people actually cared to find the volume of, which it certainly is not in the case of like a necklace or something, which is my only encounter with this shape. But if it was, you know, some piece of metal and people needed to find its volume, well, calculus would have given us a formula. In other words, those are the two variables, capital R radius and little r radius. Well, then what do you do to those two numbers? I mean, this is what algebra is about. You take those two numbers and square them and multiply times pi and divide by 3, and boom, out pops the volume. And you sort of don't even know you're doing calculus. So let's take a quick look very fast at the conceptualization of this for washers, and also just to help you with the test that is still a ways out. But the way that you want to see this is as just, well, this big slice that you take of this shape. So you got to see that, and you don't actually have to draw it three-dimensional. You could just draw it as, you know, kind of a horizontal slice like this. In other words, flat. If you can visualize it 3D, that's all the more helpful, but it's really a flat slice. And so you should think, okay, well, you know, what's this radius right here? Well, that radius is the X coordinate of the sphere. It's kind of a cool way to do it. You know, it's a lowercase or a subscript. X, that's the X coordinate of the sphere. And the important thing is that slice has to move. And so I can't give that a variable, or I can't give that a constant name. So that thing's got to move up and down. And so X has got to change. And then I look at the thickness of my slice and I realize, as we saw every time, that it's not the same letter. One's always X and one's always Y. And so great, there's that cylinder right there. Awesome. Well, what's the volume of that cylinder? The volume of that cylinder is pi times its radius squared times its height. And now I just got to add all those up while it slides around. So this is not hard to conceptualize. Well, then I look at it and I think, okay, well, that's great, but I've got X's and Y's. And so the key is the equation that creates this shape is the connection between x's and y's. And of course, that equation, as I wrote up on the top, is x squared plus y squared equals 21 squared, which I think is 441. So that's my relationship. And so what is x squared equal to? X squared is equal to 441 minus y squared. And we're very fortunate that notice, hey, that's x squared, and I'm replacing x squared. So really I have pi times 441 minus y squared dy. So awesome. Everything is y's. That's a super easy integral to take. I'm on my way. And then we come back and say, great, well, we're not actually finding the volume of a sphere. Notice this would actually give you the formula to find the volume of a sphere, this volume of a sphere formula, but we're saying, no, it's got a hole drilled in it. And that hole, the cylinder, has its own. So I'm going to draw this in now. Has its own radius. And that radius is, well, not a variable. It's 3, like all the way down. So I could call it x of c if I wanted to for x of the cylinder, but it's a constant. So like there's no reason to give it a letter name. It's going to be 3 no matter where you are. 3, 3, 3, 3, 3. So awesome. Well, what's that volume then? Well, that volume is equal to pi times its radius squared times its thickness, which is dy. So that's just 9 pi. Great. And now I'm just going to subtract those two things. So then the actual volume is to say, cool, then I've got pi times 441 minus y squared dy minus pi times 9 dy. Really, that's what I've got. Now, the one thing about this that's not obvious that some people screwed up is you got to take a look at this shape. You know, how high does this go? Well, the last slice is right here. So the highest y coordinate you get is that y coordinate right there, which Desmos rounds off for us, but it's the square root of 45. You could do Pythagorean theorem on it. If this distance right through here is the radius of 21 and that distance is 6, Pythagorean theorem on 6 and 21 gives you that height right there, which is the square root of 405 or 9 square root 5. Some of you simplified it too. Good for you. Either one. So this thing actually goes from y values, since the bead's top is missing. Remember the shape actually kind of looks like this if you were to look at it from the side. So it doesn't make it to a y value of 21. So if you go to a y value of 21, then you're saying it's a sphere, and it actually doesn't make any sense because now you can't subtract the cylinder off because the cylinder stops at 20.125. And so you got two choices. You could say, I'm going to take this all the way from the square root of 405 all the way down to the bottom, which would be the same exact spot. Or you could say, no, I'm going to do this and just double it. And a lot of times plugging 0 in will make your life a little bit easier. Anytime I plug a negative number in, I might make mistakes. And so that's just kind of cool. So that's a super easy integral to take because it's just 441y squared. And of course, you might clean this up a little bit because you can pull a pi out of everything. And you end up with 441 minus 9, which is, what is that, 432? No, it doesn't sound right. Something wrong with that? Why does 432 sound wrong to me all of a sudden? Anybody see anything wrong with that? I don't think there is, but for some reason this doesn't sound right. So that's actually a really easy integral to take. That's one of the reasons I thought this was a neat project, because you actually can do the calculus. You don't have to kind of cheat to get the answer. It's the other reason I asked for an exact answer. Now, let's try this again quickly, just for your conceptual power, with shells. I'll try to go quickly here so that we aren't wasting too much time. So with the shell, what you're saying is I would really like to kind of make a chop right here. And again, I could take that all the way down to the other shape. But what I'm really doing is taking this really skinny little slice this way. So it's kind of weird. It's like an onion. You're coming in from the top and slicing around this direction. So we said, great, well, take a look at this. Isn't that the y coordinate of the sphere? And this little slice that you're making in it right there, because it's horizontal, would be dx. Again, you have a dx and a y. They're always one is x and one is y. And then I've got this circumference all the way around, which is 2 pi r. So then what I'm really getting for that volume is when that thing is laid open, is I've got its thickness times its height times the circumference, which is 2 times pi times, well, radius. Well, what's radius? Well, that's an x coordinate. So that's the x coordinate of the sphere. And then because of the way I drew it, if I'm actually stopping it right here, then I'm going to have to also double this. Now, the cool thing about this is I don't have to subtract anything. I can just let it be whatever it wants to be. So to clean that mess up a little bit, then I say, well, I got some constants in there. I got 4 times pi. So that takes care of the 2, the pi, the 4. Then I've got a y and an x. I've got an x and a y, and I've got a dx. And so I'm really kind of stuck with the x's, or at least I have more x's than I have y's. But again, I look back at the original equation and I say, oh, cool. Well, I know how those are related. Since x squared plus y squared equals 41 squared, then that means y squared equals 441 minus x squared. And so y is the square root of 441 minus x squared. And so that's not real good. Like that's a sort of a terrifying looking equation. And so when I come back and say, okay, cool, let's find all of this multiplied out. So now I have x times the square root of 441 minus x squared dx. Everything is x's. So that doesn't look so good. Like I have this multiplication that I've got to do, and I don't like multiplications because again, I'm thinking product rule and so forth. Now, since we're dealing with x's, for what x's is this true? Again, the important thing is to see the slice sliding everywhere. Does it make sense? At one point, it's down here, like a really low, small shell. Well, notice that x makes it all the way out to 21. But the x does not go all the way to 0 because it's got to stop right here. So in a sense, this is the last one. If I throw in, to make the drawing a total mess, throw in kind of a shell right there, like that's about the end of it right there. So it's actually going from 6 to 21. So that's really nice. Like I didn't have to do any math, like it's visible in the picture. The x values are going from 6 to 21. But again, this is really neat and miraculous because although that looks really terrible, and I was looking at this, again, the reason I asked for an exact answer, because you can't really deal with junk inside of junk. Again, that has the look of, what do we call that in 251? Chain rule, like function inside of a function. It's like, ugh, if I see the chain rule, ugh. So it's actually really rare that what happens here happens. And so this is just good for your understanding. And I will want on the test, and I'll tell you, if it's like a terrible integral, I'll just tell you right up front, because you could burn an hour, 2 hours just trying to take an integral. So I'm going to tell you, take this integral by hand, because like this problem, it's just a good use of your growing skill of substitution. If you let u be 441 minus x squared, which implies then that du is negative 2x dx. So there's my conversions to the new world. All of a sudden, something beautiful happens. Remember what we said in class was kind of back in the day that, you know, when the derivative of what is here is sitting out here, that's actually really good. So watch what happens to this problem. So then you say, great, there's a 4 pi out there. So now all I have is the square root of u. So I think I'll write it as a power so that I can think power rule. That made that really easy. But then I've got this dx to get rid of. So there's still an x here. I've got this dx to get rid of. So if I solve that for dx, that's du over negative 2x. So du over negative 2x. And so, and again, this is really cool that this comes up in a real problem. That, wow, that's amazing. That's totally cool, because the one thing that I needed to get rid of was this other x and then another x here. And it's like, sweet, those are gone. So I never had to bother to get rid of that other x. It got rid of itself. And so now all of a sudden I just have u to the 1/2. And many of you got this right. And I'm just really impressed. I think that's super cool. So then I could take that -2 out in front. So now I have a negative 2 pi out there. And then all I have is u to the 1/2 du. And notice I didn't put any limits of integration. So if you want to complete this to make your life, really cool, then go ahead and just keep going and like stick in 6 for x. 6 squared is 36. 441 minus 36 is 405. And then also stick in 21. 441 minus 21 squared is 441 minus 441, which is actually 0. Some of you flip those over because you're just thinking, wait, the bottom number should be smaller than the top number. But no, let it do its work. If you flip those because you thought you must have had it backwards, you ended up with a negative volume, and you shouldn't get a negative volume or something's wrong. But notice there's a negative out in front, negative 2 pi, like that negative is going to fix this. So this is a super easy integral to take now. So it's just neat that we actually have this skill with a little bit of substitution knowledge to kind of finish this problem. So then, of course, I add 1/2, or add 1 to that, which makes it 3/2. I divide by 3/2, which is multiplying by 2/3. And then I still have this negative 2 pi out front. And then I erase it, and I put in 0, and I put in 405. So just to kind of finish it, because this is so close to being done anyway. Then I put 0 in, and I get 0. And then it's minus, and I put 405 in, and I just have 2/3 times 405 to the 3/2 power. So minus a minus becomes a plus. 2 times 2 becomes 4. So I end up with 4/3 pi times 405 to the 3/2 power. That's perfect. And that's a great answer. You're done. Perfect. That's exactly right. Some of you may know how to simplify that, which is, since that's 405 to the 3/2, it's just good for your algebra knowledge. Wouldn't that be 405 to the first times 405 to the 1/2? Don't you add exponents? So if I work backwards, then that means a 405 comes out to be multiplied by 4, which I don't know what the answer to that is. So 405 times 4 is 1620. So you could say 1620 over 3, feels like I'm doing something wrong here, times the square root, no, I'm not, times the square root of 405. Now, again, I sort of feels like that was a lot of work for nothing. And then, again, because of cool shortcuts, 1 plus 6 plus 2 adds up to 9. So I know 1620 is divisible by 3, so that's kind of nice. So if I haven't made an algebra mistake, I end up with 540 pi times the square root of 405. And the square root of 405 even simplifies down, so forth. So, again, you can play around with the algebra and try to, clean that answer up if you want to, but in the end, you get the same answer for both of them. And I hope you took that to the wall. Most of you got this question right, which is awesome. And, is that from talking to other people? But again, with these projects, you should get every point on them, because you should be asking me. If you don't get the same answer for both, don't just turn it in and say, oh, I didn't get the answer for both. Like, you should be bugging me, because I want to teach you. Like, I want you to get this under your own power, not just have to watch me do it later. Anyway, I hope that helped grow your intuition about how to draw these pictures and so forth. So let's dive into today's project, which is amazingly cool. So did you pull it up already in My Open Math? Let me just quickly introduce it to you. as I mentioned the other day, this is one of what I consider to be the coolest projects I've ever made up. Both because it's the mathematics it draws in is just neat. It draws in a diverse range of all of the things you've ever learned about math, which again is a really tall order, because to be asked to actually know everything that you're supposed to know is a lot to ask. We don't tend to remember things very well. The other part of it is it's so darn practical. As I mentioned before, that's kind of my bent. So I made a Desmos of this so that I can help you visualize the problem. And here it is. I played with it yesterday and fixed it up a little bit even. So I don't know if you know anything about basketball, but I need to teach you a little bit about it. And I think I will start by opening the problem itself up. Again, I beg you, please get full points on this. Like, please bother me until you get it. As before, I want you to work with other people. So when I shut up, I'll set up a whole bunch of breakout rooms and you can go off and do this with some other person. You don't have to turn in 2 pieces of paper. One of you turn it in My Open Math and just make sure both people's names are on it. So I found this Stromo shot of basketball, some dude out shooting hoops. I don't know if you know this or not, but the rim itself is 10 feet off the ground. That's one that's not a variable from sort of place to place. The rim is always 10 feet off the ground. And then there's some other things that are kind of cool here. Basically, what you're going to do is shoot your shot from wherever the heck you want to. I gave you some suggestions. A 3-pointer in high school is 19 3/4 feet away, whereas in college it's another foot, and in pros it's 2-3 more feet beyond that. So you can shoot a 3-pointer. For all I care, shoot it from half court, shoot 80 feet away, shoot 6 feet away. I don't care where you shoot from. But these are classics, 3-pointers. And then a free throw is 15 feet away. Maybe you can see on the ground here, that line that's a free throw. The distance from here to the center of the rim. Notice I said a free throw is 15 feet to the center of the rim, circular rim. So from that center straight down, straight back to here, right triangle, 15 feet. So you can shoot one of the classic shots that people practice a lot, or you can shoot from any place you want. Also told you here that the rim turns out to be 18 inches in diameter, which I had to look up. And the ball is just a hair over half that in its diameter. So almost 2 balls will fit through a rim. And so then you see how he let go of the ball? Like, that guy looks like maybe 6 feet tall, but he let go of the ball a couple feet over his head. So he might be releasing the ball from 6 feet plus 2 feet, like from 8 feet over his head. So you have to kind of choose where you're going to release. And then do you notice he shot what I would consider to be a fairly normal shot, which is, not too high, not too low. Let's see. I don't know if I can go in here. I don't think I'll worry about that now. But I don't know, just to guess, I would say he shot like at maybe a 50-degree angle. What does that look like to you? I don't know. I could throw a protractor on the screen and measure it. But it turns out that there is an ideal angle to shoot a basketball at. Like, if you want to have the highest probability of making it. And that's kind of what I want you to tackle in this problem. And what I'm saying here is you can choose any angle you want. And when I mean angle, I mean this angle right here. That purple one looks like about, well, I guess I said over here, 40 degrees. So that angle right there from here to here is 40 degrees, or the blue one is 60, or the red one is 70. You can shoot any angle you want. Just pick one and shoot the ball. So pick a distance. Notice this particular shooter let go of the ball, 0, looks like 7 feet. Let go of the ball 7 feet in the air. And you can tell what their shot length is. It's out there at 20, and then that looks like 20 3/4. So if I remember right, that was a high school 3-pointer. So this is a high school 3-pointer releasing the ball from 7 feet in the air. And so the only thing you know for sure if you make the basket is at one time the ball was here at 0.7, and then at another time it was here, and in this case 20.7510. Those are the 2 ordered pairs, And then we started playing around yesterday with, how would you find the equation of that parabola? So let me show you some cool things with Desmos. So do you see what you're looking at now? This represents the rim. There's the front of the rim, there's the back of the rim, and you're trying to get the ball to fly through the rim. But I want you to notice something. This shot right here is at a theta is 35-degree angle. That is really low in basketball. If you've ever watched, even in passing, somebody shoot a basket, do they shoot that flat? The answer is no. Watch why. And that ball, this ball is the proper size, 9.5-inch diameter. Watch what happens when it flies over to the rim. What happens?
It bounces off the rim.
It's actually hitting the rim. Like if you shoot at 35, you're not going to make the basket. Do you understand that? Now there's a sort of an idiotic exception, which is if you hit the bar at the right height, it'll pop up in the air and then drop through the hole. But obviously that'd be dumb. Like if you made that, you're a miracle worker. So nobody ever shoots at 35 degrees. Does that make sense? Shaq, as I mentioned yesterday, was kind of a famously terrible free throw shooter, and he shot super flat. I think it was 45 degrees that I measured one time when I gave a talk about this to a bunch of nerdy math teachers. And can you see that it is possible to make it at 45 degrees? See how it just barely clears the front of the rim, and then look at the back, barely clears the back of the rim. That's why he was so terrible. I mean, does it make sense if you said, I'm going to shoot this at 45 degrees, then you have almost 0 degrees of freedom. Like you better shoot it at exactly at 45 or it will not go in. And of course you got to get the speed right. I mean, you have to get the speed of your shot exactly right to even get it to follow this path. So his free throw percentage was just terrible. So you can't shoot a basketball at 45 degrees and be any good at this game. So let me ask you a question then. Why wouldn't you want to shoot it at 80 degrees? Notice how nice, you see how easily the ball fits through the rim right there? See how there's all this room to spare? I mean, how much is that? I can't, what are my squares worth down here? I don't want to take the time to figure it out. But you see how there's all these degrees of freedom. Like you can miss your target here by a mile, and there's just all this room. But why wouldn't you want to do it that way?
Because it would take quite a bit of effort. You'd have to throw it really high into the air.
Even worse than that, you're right. I mean, you'd almost have to like rear back and throw it. And of course, look, it went 35 feet in the air, it like hit the gym ceiling or whatever. But if you're outside, although you have a ton of degrees of freedom down here, what's wrong with, well, the shot being so long?
It's also harder to keep accurate with that length.
Yeah. I mean, does it make sense if you're trying to throw like your piece of paper into the garbage across the room and you throw it over there? Well, what happens if that garbage can is not across the room, but it's now down at the street? Like it's so far away. Does it make sense your degrees of freedom are now really tiny? So that shot is way too long. Now, perhaps you can see why I'm giving you this project now, because you now know something about arc length, which means you can actually figure out how long that shot is right there. You can figure out that length of shot right there. How long is that distance actually flying? So it's this combination. And so again, think of like a piece of paper in your bedroom or whatever, and you're throwing it in the garbage. Would you rather have like a big garbage can that was a long ways away? Or would you rather have a tiny garbage can, like my coffee cup right here, but it was like right in front of you? Tiny close or big far? Does it make sense? Those are kind of the same. But in this case, you're throwing it at kind of an angle. And so the question is, which one gives you the most degrees of freedom? It turns out that there's actually a right answer to this. In the end, if you take this length right here and you take that distance right there, which is how much freedom you have, if you take those two distances, which you can calculate, and you do what I did right here, which is kind of think of it as a right triangle. So this air right here is how far the ball has to work back and forth inside the rim. Like you can miss your projected dotted line. How much air do you have? And then what's the length of the shot? If you figured out this angle, which I called phi right here, PHI. That's not a Greek letter that you've seen for an angle too many times. I think it's pronounced phi, PHI. If I took the tangent of that, I could actually find out what that angle is. Does it make sense? In the end, what you need is the biggest degrees of freedom possible. That's really what I want you to calculate, is just to make up an angle, figure out the path of the shot, and then figure out figure out what that phi is, that degrees of freedom you have. And in the end, this should impress you that if you're shooting, say, a 3-pointer, no wonder that's so hard to make that shot. So maybe I'm, if you will, as I said before, I'm aiming, I'll say, for a, I don't know, how about a 58-degree shot? I'm going to shoot it at 58 degrees. Well, I would ask you right now to just kind of guess in your mind. So you're not going to actually pull it off, right? You're not actually going to shoot at 50 degrees. But the question is, how many degrees of freedom do you have? Do you have 1 degree of freedom? Which means as long as you shoot it from 58, well, down to 57 or up to 59. In other words, if you shoot anywhere from 57 to 59, you have 1 degree of freedom, then you'll still make it. Does it make sense? You got to have some room for air, and the ball is a lot smaller than the rim. And so that's the point. How much is it? Is it 1 degree? Do you think that's realistic, or is it more like 2 degrees, or is it more like 0.1 degrees, or, how many degrees of freedom do you have? Well, do you see that that's a function of, notice this is a much shorter shot. That's good. But because it's such a low angle, you have sort of much less room for error. If I back the ball up, that distance right there, is kind of your E, your error in my right triangle a minute ago. What's that error right there? How much is that distance? So if I choose a higher angle, then that error distance gets bigger, and that's good. But unfortunately, your distance of your shot just got longer too. And so where's the bigger question is, what's the best angle to shoot at? But this is a fairly involved problem. So really what I want you to do to back up is full credit, choose a shot length. And again, in this picture, that's 20.75. I don't care what your shot length is. And a release height, H, I chose 7 feet over here. And a release angle. Again, that purple one is 40 degrees. And then develop the resulting quadratic equation to model the flight of the ball. In other words, find that equation that models that. Awesome. Then use that equation to determine the degree of tolerance, the degrees of freedom, that phi that results based on the arc length of the shot, which you now know how to calculate, the arc length of that part of the curve. Notice that would be the arc length formula that we looked at yesterday, and the error in inches at the rim. So I don't care if your shot is really good. Now, if you really like this problem, and I'm almost going to tell you, like, please don't do this. But if you really get interested in this problem, like maybe you actually like basketball and have played it before, this is just one of these problems that gets under your skin, then you could go back and try it again. What's kind of cool is to say, okay, well, I succeeded at 40 degrees and I got a degree of freedom, say half a degree. Well, then go back and do it at 60 degrees. And then do you get a bigger degree of freedom? Is it not a half degree, but now it's a 1 degree of freedom? Like that would make that a better shot. So the bigger question here is what angle should you be shooting at? And there is actually a right answer to that question. And it turns out the best shooters in the NBA just naturally shoot at that angle, because that's why you made it to the NBA. I doubt anybody taught them calculus, or I've never even seen this even discussed anyplace, which again is why I think it's a neat problem, because it's not something I heard anywhere. I can't remember why this came up in my brain. I think it had to do with Shaq being such a terrible free throw shooter and kind of wondering why. Any questions about that? Do you feel like you at least understand how to get started?
I have a question so we're trying to find the parabola that the ball travels, right?
Yeah. Find the equation of that parabola. And the only reason you're finding that is because if you don't have its equation, then you're not going to be able to find that arc length, which again is why this problem is so cool. Like we're not finding the equation of the parabola because we're a nerd at the basketball game and we don't like basketball, but we just like math. And so let's find the equation of the flight. Why I think this problem is so cool is because finding that equation, you can now find the arc length, and that arc length actually gives you a way to analyze what the best angle to shoot at is. So let's do this. Let's stay together in a larger group while you start playing around with this a little bit, just for a few minutes while at least you feel like you got to start. But again, I want you to go off. I would far prefer that you work with somebody on this, just to cut down the amount of work, also so that you bounce ideas off of each other. Again, my goal would be every single one of you gets all the points for this assignment because you just keep asking me. It's a fairly hard problem. It's fairly involved. And I'm going to need to talk to you before class is over a little bit more about this error thing. Like, how do you figure out how far away the ball is from the edge of the rim? Because that's one of the harder calculations here.
I am really not sure how to start trying to find the equation of the parabola.
Yeah. And so again, I showed you something about it yesterday, and I don't just want to tell you, but I also don't want to leave you just sitting there staring and having no idea. So I will give you a sort of a, I don't know, brief intro to that concept. So I'd say start by just picking something. Pick your H. What height am I going to shoot from? So now you have the coordinates of where this parabola takes off. So again, 0, 7, 0, 8, 0, 2. Kick it from the ground now for all I care. It's 1 foot off the ground and you kicked it in. You like soccer better. Good for you. But I said choose between 5 and 9 because that would be where the average person has the, like no human can really shoot from a different angle than that if you're like actually playing basketball. So if you want it to be realistic, pick H to be from 5 to 9, but I really don't care. And then choose an angle. And as I said before, don't pick 35 because it's not going in. Like you got to pick an angle that's big enough that it actually has a shot at going in. So I'd pick, I think 40 degrees is even pushing it. I don't know. Let's go look. Let's take a quick look at the graph. If you pick 40, notice the ball hits the rim, so don't pick 40. Like 40 is not going in. Now it does depend on the length of your shot, and my Desmos is kind of fun because I actually can change that on the fly, and it just remakes the problem. Except for my ball just disappeared. I don't know why my ball disappeared. Oh, it's flying its way out there somewhere. Notice how if you're really close like this, that changes things. Like if you were this close to the rim, you're shooting an 8-foot shot, then you got to shoot way higher than. So for now, just shoot a, notice that will fit. The ball's going to fit through the rim at that 70-degree angle if you shoot an 8-foot shot. But you got to shoot a lot higher if you're closer to the rim. So stay away from low angles. Like pick at least 50, I think. And of course, you can shoot from a higher angle. I just moved it up to 8 feet. If you're taller and you release the ball higher, that actually makes it easier to make a basket. If you're short and you're shooting from really low, that's actually worse. Your chances of making it go down. So one of the other reasons I really like this problem is even if your goal was just to find the equation of the parabola that follows it, like it actually takes calculus to find that. I just think that is so cool that you actually need calculus for something practical. So I'd like to, I showed you this yesterday to some extent. I mean, I sort of completely showed it to you yesterday, but I'd like to give you a little bit of time to think just to see if you can pull this off yourself. But so if I choose the release point 0.8, and I'm going to put the rim out here, you have no choice but to put the rim at something 10, because you have, everybody should have 10 there for the y coordinate, because that's how tall the rim is. So then if I decided to shoot a 17-foot shot, okay, so you need to pick those two things, and I don't care what you pick except for the 10. And the next thing you've got to choose is that theta. So I'm randomly saying, okay, 52 degrees. And again, you're thinking of the ball as a dot flying through the air. But the thing that's really important to understand is, although you aimed at 52 degrees, does it make sense that the ball falls away from that very quickly? In other words, it doesn't stay that way. So that's the equation you're after. From your algebra knowledge, if I'd given you 3 points, I don't remember who said this, it might have been Cheyenne yesterday, but was saying like that maximum point up there was always really important. But unfortunately, we don't know where that is. And because you're shooting from low to high, it is not in the middle. In other words, that is not going to be at 17/2, since I have a 17-foot shot. That's not going to be halfway. Can you see that that's the case? So unfortunately, you don't know where that is. If you had 3 ordered pairs, then you could find this equation using 3 equations, 3 unknowns in the matrix function of your calculator, but you don't. You know 2 ordered pairs, and you know the angle that it left at. So what I said yesterday was, well, don't all parabolas look like this? So the question is, how do you find those constants A, B, and C?
Well, the thing that we figured out that the tangent is the slope.
Yeah, so let's take a look at, let me just refresh your memory. I'm going to rename this, instead of y, I'm going to call it P of X, path. The path of the ball is a function of X. Does it make sense? You sort of know, this is really powerful. And again, if you leave math not being able to speak this language, like that's a bummer. If you actually want to make some money as a result of your math knowledge, it's not going to be because you can get question 17 right in some boring section in a math book. It's going to be because you can speak the language of algebra. And that's why I give these projects. And although they hurt, they make you stronger. So what do you know? Like what has to be true algebraically? Well, 1, P of 0 has to be 8. Check. Like that's one fact. In other words, the point 0.08 has to work in that equation. Secondly, doesn't the point 1710 have to work? So P of 17, when X is 17, that equation better spit out 10.
We also know that the P of 0, the derivative of that is going to be equal to 52 degrees.
Exactly. So Justin mentioned that, Dominic mentioned that. The third thing that you know is P prime of 0. Remember what that means is slope, the slope of the curve. You know the slope of the curve. Now it's not 52 because 52 is not a slope. So modify that a little bit, Dominic. That's not the slope, it's the angle. How do you connect the slope and the angle?
Oh, what is I forget the conversion from degrees to radians.
It's not even that. If this is 52 degrees, do you agree that that makes a right triangle?
Yeah, then you're calculating the rise and run from that, which is the
Yeah.
slope.
Whereas the slope is actually the rise over the run. So 52 degrees is related to the slope, but
Oh,
it isn't
yeah.
the slope. Does it make sense that the tangent of 52 degrees is equal to opposite over adjacent? So actually the tangent. It's the tangent of the angle that actually is equal to the slope. Not just 52 degrees. Now, again, in one sense, I would say you should know that. You took Calc 1. But we don't teach calculus this way. We don't teach it deeply enough that you can actually use it for something. I try to, but that's a big ask, I think. Do you understand calc well enough to actually to make that connection? As I mentioned before, we call this line the tangent line. That line is tangent to the curve right there. That's why it's called a tangent, because it's related to trig. That's why the word tangent even exists. That's why somebody picked the name tangent. What should we call the opposite divided by the adjacent? Somebody said, let's call it tangent, since if I have a curve and the graph just touches it, that curve is called tangent. So knowing these three glorious facts, you actually know everything you need to be able to find A, B, and C. Now, what you should do is, once you find A, B, and C, is graph it on Desmos or on your graphing calculator and make sure it does what it appears to do. Like, does it actually go through the point 0.08 and 1710? Because then you kind of know, oh, sweet, I actually got it right. And now that you have the equation, you can find the arc length. And by the way, the integral that you need to take, remember the integral for arc length is the square root of 1 plus, in my case, p prime of x squared dx. You're not going to be able to take that integral. This is not like the previous project where that integral, oh yeah, you can take it algebraically. It can be taken. You're not good enough at integration to do it just yet. You will be before this class is over with. And again, if you're like a glutton for punishment and can't wait because you think this is a cool problem and you want to talk about it one-on-one outside of class and just think about it a little bit because your brain isn't full with your other classes and all that stuff, more than happy to teach it to you now while it's maybe interesting to you. But cheat to get that integral. And then do what you can to kind of see, does that make sense? Does it look right? Does it look reasonable? Again, I am more than happy to tell you the answer. If you say, hey, I made it this far, is this right? To me, you're nuts if you don't ask me that. You should get all the points on this. Ask me, is this right? Yep. Nope. Why is it wrong? Okay, well, let's talk about it. Okay, I'm going to set up, since I vaguely understand how to do this now, I'm going to set up like I'm going to set up 10 breakout rooms. And if you either send me a chat or you just tell me out loud, hey, so-and-so and I would like to work together, or you say, hey, does anybody want to work with me? I would encourage you to not just work with people that you know, like meet new people. work with somebody else. Like there's no harm in working with somebody else. All it does is help you because I don't care if you're the smartest one and the other person is really slow. Like if you bounce ideas off other people, and I'd like the groups to not be bigger than 3 just because I want everybody to feel like they're a participating member. And then I think you can send me from those break rooms. I think I'm going to stay in the main room. You can send me a message that says, hey, we got a question, and I'll know, oh, you're in breakout room 3. And then I'll just pop over there and discuss it with you. And you are welcome to work alone if you want to, because you'd like to get it into your own power. If I get that too. I'm going to bring back up the page that I just made.